4. Hello and welcome back to Calculus 2. So the storm is over, right? The Hurricane 1 passed. And now we're going to talk about integration. In chapter 7, we are learning about methods of integration. So you know how derivatives had product rule and chain rule and quotient rule and all that kind of stuff. We are going to have now integration techniques, and we're going to study a few of those and some numerics, and I also have one lecture on differential equations. It's just not even a tip of the iceberg. I don't know. Three molecules of ice. That's how much we're going to do, right, off of the iceberg. It's 3 molecules in terms of differential equations. So integration by parts is the first. This is one of the most powerful and most used techniques. You are going to see this over and over again in your later coursework when you transfer out to 4-year and start doing your engineering classes. This integration technique is one of the most frequent. Also, for those of you thinking of, mathematics, either education or something, you want to maybe go to graduate school. In the hallways of universities, there's this little saying that says, when in doubt, integrate by parts. That's how important this thing is. So pay attention, right? We start by realizing what integration by parts is, and that is backwards product rule. So in your Calculus 1, your instructor hopefully told you that chain rule and U sub undo each other. Well, now integration by parts and product rule create that pair. That means that we can derive the formula for integration by parts from basic formula of product rule. If I write the derivative of U times V is equal to U dV dx plus V du dx, which is the standard formula for product rule, you can quickly see what happens if you integrate this. If you integrate this dx everywhere, you see that on the right-hand side, the derivative and integral cancel completely. So you are just left with U times V. So that's on the left-hand side. On the right-hand side, only these dx's cancel, and you are left with integral of U dV plus the integral of V du. And now you solve for integral of U dV as U times V minus integral of V du. This formula is known as integration by parts. Now you are memorizing this formula. You also have that this is U, that U is U of x and V is V of x, right? So we know those are functions. There is another way to understand and visually connect this formula. So this is derivation slash proof number 2. Say you have some function in the UV coordinate system, and say you are looking to integrate this. So this is the function v of x, right? Observe that you have area 1 and area 2. So now, if you draw vertical representative rectangle, you see that area 1 is given by the integral of v, and du is the input. If you look at area 2, which has the horizontal representative rectangle, you see that that representative rectangle is dv. So you have integral of u dv in that case. And you also see that the entire area, the total area AT, is u times v So what do you have now? You have that the total area is the sum of the two smaller areas, which is u dot v is equal to integral of v du plus integral of u dv. Solve for integral of u dv, and you get the same thing as before. You get integration by parts. So you are going to memorize this formula, and then by practicing problems you will develop the sense of when you get to use this one. What happened? All right. So now let's see how does this thing work. One of the standard examples is to start with x sine x dx. All right, so what I need to pick is u and dv, and I need to compute du and v. So I need to pick u dv. And now, hopefully, when you are looking at the formula, you see why you need to pick u and dv. Because this integral represents this. And this is the solution. So you will break these things up in some way. Obviously, dx always belongs to dv. But then you can also pick x with it, or sine x with it, or both, depending on the problem. So you have to develop. And your next lab, which you should start tomorrow 6 a.m., is going to address that, of how to pick, what to pick, and it's going to make you choose wrong, make you choose right, and then write a paragraph on what went wrong and why is the other one right. The next lab really helps with this a lot. So what am I going to do? I'm going to pick u to be x. Because when I differentiate that x, it's going to die. Right? Derivative of x is 1. So it disappears. And I'm going to leave, since I picked u to be x, then sine x dx must be the leftover for dv. And to get, how do you get v out of dv? You integrate. Very good. You integrate. So if you integrate both sides, the integral of sine x is very good. Negative cosine. Now you don't have to put plus c, because there will be a plus c at the end of the problem. So now you see what we have. We pick u and dv, and we compute du and v. So those are always set in stone. As soon as you make a choice for the first two, second two have to be the derivative and the integral, whatever it gives. And if it doesn't fit, you have to make different choices. You cannot go and fix within this and pick different, right? You can, all you can do is you pick different u and different dv. Look. Over here you take the derivative because you are going from u to du, and on this side you're integrating because you are going from dv into v. And now here's the $1 million trick. This arrow. That arrow gives you the formula. You see that? U times v minus this. So if you write it in this fashion, you just put the arrow, it immediately gives you the formula. So what do we get? We get negative x cosine x minus the integral of negative cosine x dx, which is negative x cosine x plus the integral of cosine x dx. Look, we can integrate, right? This x that was making an issue earlier is gone because it died in this derivative. So now we can integrate this piece, and we get negative x cosine x minus the integral of cosine is, oh sorry, plus. Integral of cosine is positive sine x plus c. So if you want to put the positive term first, you can say sine x minus x cosine x plus c. So this is your introductory example, and this is probably the shortest problem you can find. Well, there's a shorter problem with e to the x. So I'm going to challenge you now to integrate x times e to the x. Yeah, I switched these two to put the positive term first. You don't have to do it. You can box this one and perfectly fine. It's just my OCD is, you know, kicking in. And all right, let's see. Yes, the entire section is the same way. Pick u, pick dv. All right. So the same procedure. U equals x, dv equals e to the x dx, and then du equals dx when you differentiate, and v equals just e to the x when you integrate. Put our green arrow there. See what I did there? Which is now x e to the x minus integral of e to the x dx, which we can integrate. And if you want to be fancy, you can factor. Right, another one.
By 2, 3.
Did you hit the brick wall? Yeah, you did, right? Because you tried to choose x to be u, right? And it didn't work. You see, one of the tricks you learned immediately. Things that you can't integrate yet, don't pick them as your dv, right? You don't know how to integrate ln. Yes, but we didn't learn that yet. So you start by picking what we did before, and then you realize it doesn't work, right? You pick this way, and you say, oh, okay, du is equal to dx, and then you go v equals, oh, what the hell is the integral of ln? And you realize you don't know it. So you can't do that. That means pick something else. All right, so scrap this, and then put ln here, because you can differentiate that. There we go. And then put x here, which is going to be x squared over 2. You see what happened? So now you put this together and see if it works. Hopefully it does. So u times v, which is 1/2 x squared ln x, minus the integral of 1/2 x squared times 1 over x dx. dv is always on top, v is always on the bottom. So this is equal to 1/2 x squared ln x minus 1/2 integral of x dx. Whew, we can do this. One half x squared ln x minus 1/4 x squared plus c, right? Because you're going to get x squared over 2, and then half times over 2 is going to be 1/4. And if you want to be fancy, obviously, you kick out 1/2 x squared. And you are left with ln x minus 1/2 plus c. When you integrate x, you get x squared over 2, and then you have a half. So that gives us a quarter, right? Beautiful. So we learned that it's not always the case that you choose polynomial to be u. Sometimes it doesn't work, And then you have to switch things out a bit. Now, Ryan mentioned that we should learn the integral of ln. So let's learn the integral of ln. You have to pick u and dv, and then compute du and v. What should we choose for u? ln x, because we can differentiate that, right? And what's dv? Just dx, right? If you took this out as u, what's left is just dx. Now, what's the integral of dx? X. Do the formula. So we have x ln x minus the integral of x times 1 over x dx. I forgot dx over here. Wow. So this is x ln x minus integral of dx. And how much is integral of dx? X plus c. And if you want to factor out x, you can. Either form is fine. Questions, concerns? All right, let's take a look at the next one. How about this? What should I do? What's u? Anyone? What's u? You can't have u to be dx. Because you can differentiate this, right? Do you remember this integral from your exam? It was a shell method one. There was exact integral on your exam. Whatever the shell question is. Question 5? 4? 5? Yeah. It was just this. You need to know this from Calc 1, how to integrate. How do I integrate this one? U sub. So we have u equals 1 plus x squared du equals 2x dx. I don't have a 2, so we put 1/2 and 2 in. Go from there. So x tangent inverse of x minus 1/2 integral of du over u, which is x tangent inverse of x minus 1/2 ln absolute value u, which is 1 plus x squared plus c. Now we do not need absolute values in this case because x squared is always positive, plus 1 is always positive, so we actually don't need absolute values. But most of the time you do. It looks so simple when I do it, right? When you try it. It's called practice. Or I can go with the truth be. I was born divine knowing all of this stuff. And I don't bleed when you cut me either. So pay attention. You pick which one is more likely that happened. I was born knowing this, or I was born not knowing it, and at one point I learned it. So you have.
Religion.
I'm sorry?
You could start a new religion, Calc.
Yeah, I already have an awesome idea for that. No one does it yet. The drive-through confessions. I would wreck money on that one, man. You don't even have to get a car. You don't even have to forget about the emissions. Just leave the car on. Push the button. On the other side, I just say, "Tell me what I need to know." And yes. Yes. I'll go like this: dx over 1 plus x squared. All right, let's pick up something from the textbook because we can. Yeah, I know you want one of these. Ooh. Huh. Is it too early for something like this? I would say no. It's never too early. Let's see. X sine x cosine x dx. Good luck. All right, let's take a look at this problem. So we see that we have 4 different factors here that are multiplied, right? It's x times sine x times cosine x times dx. Now we know that dx must belong to du part. That's sorry, dv part. And we know that we can differentiate everything and anything. So the question is, what can we integrate? When you have questions like this, you try stuff, which is why I gave you a little bit longer than usual. And if you fail, you redo it differently. So when I pick u, I'll pick x, and dv is going to be sine x cosine x dx. Now when I differentiate du, I get dx. And over here, what do I have to do? How do I integrate this? No, by parts. U sub. Yep, basic U sub. So there's a U sub within by parts. It's coming up. So when we do U sub here, right, you pick U to be sine x and du to be cosine x dx. You quickly see that you get 1/2 sine squared x dx. And now you use the formula, and the problem is, oops, u times v, so it's 1/2 x sine squared x, there's no dx here, minus 1/2 integral sine squared x dx. Now what? Anyone? Yes. The only way you can integrate this is if you know power reducing from trig identities. If you don't know power reducing, you skip to the next question. So formula that you must know is sine squared x. We covered this on the day 1. 1 minus cosine 2x over 2. So 1/2 x sine squared x minus 1/4 integral 1 minus cosine 2x dx. 1/2 x sine squared x minus 1/4 x minus sine 2x over 2 plus c. We can write this as 1/2 x sine squared x minus 1/4 x plus 1/8 sine 2x plus c. It's getting spicy, right? So after our after our integration by parts, we've seen that we have to do U sub within the by parts part. And then we also had to use the power reducing formula to be able to finish off the problem. All right, Chris came up with a different solution, which is amazing. So let's take a look. I want to call it way 2. Other way. So what he used is the fact that sine 2x is 2 sine x cosine x. And our problem, x sine x cosine x dx, has this string. You don't have a 2. Well, you can fix that, right? And now the problem becomes 1/2 integral x sine 2x dx. Well, that's something that we can deal with u sub, and it's not going to involve crazy u sub within by parts. So u equals, let's call it 1/2 x, and then dv equals sine 2x dx. du is going to be 1/2 dx, and v is negative cosine 2x over 2 plus c. We don't need that. Use the formula. So this is the same problem. So what do I have? I have negative 1/4 x cosine 2x. Minus and minus gives me plus 1/4 integral of cosine 2x dx. There we go. It's all good. And now we integrate the cosine here. So negative 1/4 x cosine 2x plus 1/8 sine, integral of cosine sine 2x plus c. Cool, right? Now you might scream, but that doesn't look the same, right? Well, trig identities, and this could be an awesome exercise for you at home to show that these two answers are exactly the same. You would be using trig identities. You have Pythagorean identity with squares, and you have also the, factoring and stuff. So you'll figure it out if you're interested, obviously. These two answers are the same. They look different. It's like same you with a different shirt today. Sometimes you have to do integration by parts 2 or 3 or 4 or 10 times, depending on the problem. So how about x squared cosine x dx? So what have you seen after you did the integration by parts? That you have to do another one. Exactly. So you have to do 2 in a row. So the first integration by parts, u equals with px squared. dv is cosine x dx. du is 2x dx. And v is sine x. And then we do the arrow. So now this becomes x squared sine x minus 2 integral x sine x dx. And now you see that this one is like the first problem we did, right? This is our first problem. So I'm going to over here underline this and say integration by parts again. So we have u equal x, dv equal sine x dx, du equal dx, and v equals negative cosine x. Arrow again. So I have x squared sine x minus 2, and now I have negative x cosine x minus and minus is plus integral of cosine x dx. So it's busy. It's just a lot of writing. Yay, finally. If the problem said x to the 4th e to the x, how many integration by part? 4. First integration by parts is going to put x to the 4th down to x cubed. And then the next one to x squared, the next one to x, and the following one kills the x. So you will have to, if the problem starts as x to the 4th, you have to do 4 integration by parts. If the problem is x squared or something, then you do Let's take a look at the problem with limits. Integral x squared ln x dx from 1 to e squared.
Ooh, I canoe. Caramel.
Thank you.
Want some more?
Oh, thank you. One is enough. So what's our u? ln x. Nice. That was evil of me, right? To put the question with x squared. So, Chris will talk about something during the SI session eventually, about some acronym that you guys can use. Something like PEMDAS, but he helps with this stuff. So. Look him up. Who?
I don't care about the pronunciation, it's just the acronym, what it stands for.
Like PEMDAS. Good. All right, let's take a look. U equals ln x, dv equals x squared dx, du equals dx over x, and v equals x cubed over 3. And the green arrow. Anyone follows green arrow? All right, good. That's points for the next test. So we have 1/3 x cubed ln x minus integral 1/3 x cubed 1 over x dx. Now we still have limits 1 to e squared, and this one needs to be computed 1 to e squared. Next order of business, compute the other integral, because I want to factor and then compute stuff. Actually, I'll put overall. Minus 1/3, this is x squared, so it's going to be 1/9 x cubed, plus e, computed from 1 to e squared. One half? I'm not sure what you're talking about. It's clearly 1/3 if you're talking about this one. Thank you. So now, what can I factor out? I can factor out 1/3 x cubed, and what's left is ln x minus 1/3. Computed from 1 to e squared. Nice. When I plug in e squared, I get 1/3 e to the 6. And then ln e squared is just 2 minus 1/3. And then minus, when I plug in 1, I get 1/3 times negative 1/3, because ln of 1 is 0. And it's not minus 1/3, it's plus 1. No, I used the minus here. I just overheated, I think. I want to swap this into a plus, and then I don't want to swap this, and then I lost my train of thoughts. I started thinking about something else. So now I have to start from scratch. So when I plug in e squared, I get 1/3 e to the 6, and then this is 2 minus 1/3. Minus, when I plug in 1 over here, I get 1/3 times 0 minus 1. Yeah, it's good. So now, 2, so 5/9 e to the 6 minus plus 1 over 9. And that's it. So if you want to be fancy, you kick out 1 over 9, and you have 5 e to the 6 plus 1. That's exact answer. You can go and get the decimals if you want to, but this is exact. Ready for a cool problem? Problem 40 says find volume of a solid revolving around x-axis with function given by sine x on domain. Oh, sorry, it's revolved around y-axis. Revolved around y-axis on the domain 0 to pi. No pressure, you have 18 seconds. All right, so let's see. We know that all of these, we start with a sketch. So this is the 0 to pi bump for sine function. We are rotating on y-axis. So which method do we have to use? Shell. Nice. So shell method says that we have to integrate from what to what? 0 to pi. I forgot 2 pi in front. And then what do I write? X sine x dx. See? Right on the integration by parts. So now unleash the standard procedure. So we have 2 pi that multiplies everything. Negative x cosine x. Minus and minus gives me plus integral of cosine x dx. So now we apply this 2 pi so we don't have to keep copying parentheses. What's integral of cosine? Very good. Computed what? 0 to pi. So when you plug in pi, cosine of pi is what? -1. So we have do what? Yes. I was about to draw this one. So 2 pi squared. Here's problem 40 in the textbook. If I have y rotation using shell method, we need parallel representative rectangle, and that is dx, right? Because perpendicular to the x-axis. So we are setting up dx integral. We have x sine x dx, break it apart, do it twice. I mean, compute the limits, not do it twice. Another example, or you're good? One more? That's the spirit. Nice. Let's find something to match your enthusiasm. Integral 1 to e of ln 2x dx. What's u? And what's dv? And what's du? dx. And what's v? All right, go on. Over here? Well, when you're taking the derivative, this goes down. It's 2x. But the derivative of 2x is 2. Alarming number of people did not know that the derivative of ln x is f prime over f. That's Calc 1, and we reviewed this in 6.8. That's the last question on the exam. I have a lot of people trying to figure out the U sub and trying to figure out some. It clearly says words and symbols. Take the derivative. What U sub? U sub.
Did anyone miss an exam? Oh. Not for you.
Choices. Oh no, it's perfect.
What?
Oh, I'll explain it after the class. It's easy. You'll know exactly why. So we have what? We have e to the ln 2e, I mean e times ln 2e minus e, and then minus, when you plug in 1, ln 2, and minus is plus 1. Now this guy over here is ln 2 plus ln e. So I have e ln 2 plus e ln e is 1, right? And then minus e minus ln 2 plus 1. Now these die, and you can factor out ln e from these two. Sorry, ln 2. You get e minus 1 and then plus 1. That's exact. So I put b minus f over, yes.
What do you do with it? On this part, after that, of 2 for after that,
You mean ln 2e? We use the formula where the multiplication splits into addition of 2 log. And then e times the first one and e times the second one, but ln e is 1, so e times 1 is just e.
after that, after e is the next one, we come to the triangle, and then you subtract 2, you know?
So when I break this apart, right, this is 1. So I have e times ln 2 and e times 1. So that's these two. And then I copy minus e. Then I copy this one, and I copy this one.
But I thought that in that point, e and ln x, they cancel each other, no?
E and ln x. Here?
Or then where you put
Over here?
e times natural log of 2e.
Over here.
They don't cancel each other even if go off.
No, nothing cancels until you write it separately, because it has two. If the 2 was a square, you put it outside and then becomes 1. But this is the only one that cancels down to 1. And that takes care of that. So now you have E ln2 plus E minus ln2 plus 1. E's go away, so you have factor out ln2, you have E minus 1 and then plus 1. And that's it. Before we hit the break, talk about evil problems. Matt, you're not happy. Oh, so you're looking for the thing, all right. Diego, you got it, right? You got it. Ready? I know. Now the interesting thing is that these evil problems can be done in 2 steps if you're using complex variables. But we don't use complex variables here, therefore start a new page, right? Can anyone anticipate the issue with this? Yes. Yeah. If you integrate or differentiate e to the x, it stays as e to the x. And what happens with the sine x as you differentiate or integrate? Yeah, but it cycles, right, as well. So when you look at this, no matter what you pick for either u or dv, you don't get to get rid of anything. First time I saw this as a student, I said, whoa. We just, you know, it's a hit like the infinite loop, right? And let's see what we can do. So, by parts. So what happens? Negative e to the x cosine x, and then plus integral of e to the x cosine x dx. We made 0 progress, right? If you look at all previous cases, after doing integration by part, we were in a better position. right? You either eliminated one of the two functions completely, or you brought it one step closer to elimination. We technically did not achieve anything here by doing this, right? Now, what's the definition of insanity? Yeah, doing the same thing over and over again, expecting a different outcome. All right, let's certify insane over here. Do it again. What happened? Back where we started. You see also extra stuff, right? Nice. What do you do when you have a situation like this? They are already equal to each other.
No,
I can't zoom in.
For the problem.
No, I'm asking what's happening here.
We'll bring the x over to the other side.
Which one?
Probably negative.
Yeah. So you plus x on both sides, right? And you get 2x equals 3. And then you divide by 2 to get 3 halves. Right? See this thing? Is equal to that thing. And this thing is your x. So you are bringing this one to the left side and make 2 of them. If you learn mathematics by form, not problem by problem, you will not be able to distinguish between these two situations because they're the same. Over there you have more writing, but writing this and writing that is the same situation. I can give you another example. There we go. It's another example of the same. This is the same as this, is the same as that. But it's mathematical form. And they all solve the same way. So, what we realize is that this part and this part are the same on opposite sides of the equal sign. So I will bring this to the other side. What do I get? I get 2 integrals of e to the x sine x is equal to negative e to the x. Well, actually I can factor out e to the x and just have sine x minus cosine x. And do what now? Divide both sides by 2. The x is there, you just can't see it because you haven't gone to the eye doctor yet. Divide both sides. One of my favorite questions. Guys, do you understand that someone came up with this? Someone sat down and figured it out. Can you just stop with your life for a second and realize that? What happened?
How long do you think it takes to figure it out?
I don't know. I don't know who did this. But someone said, I got nothing from doing integration by parts. Let me do it one more time. Do you understand that someone actually had to think of that thing? Right? It didn't work. Let me do it again. And then, whoo.
How far this rabbit hole goes.
Yeah, exactly. So this is one of the first times when I was truly blown away by, you know, human capabilities and yeah.
My Calc 1 professor did this for the second problem for your introduction for integration of parts back in high school, and first he came up with X, each of the X's, the first problem, he demonstrated it, and then he's like, all right, you guys try doing this one, he gave us this. And we were just like so baffled. It took us like 10 minutes until he actually went over it, and then he was like, dude, he's like this.
Yeah, but at that point he never said that you can do integration with parts multiple times and so on. Yeah. So eventually, those of you interested in mathematics might go to graduate school and then learn some linear operators where you're going to have to do 4 nested integration by parts as operator and then apply that to a general type of a function. And you know, there's a lot of terms there, but the more these things you do, the more you notice the common themes and things that pop out. So, as I said before, practice, 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 practice. And as you're running, when you hit the brick wall, turn around, run the other way. That means you choose different combination for your U and dV. And the most important part, do not give up. Because there are just finite amount of things that you can try. And, you know, it's just the attitude towards the whole thing. Oh, I didn't get it on the first try, so I quit. Yeah, you're 12, right? So you can't do that. You can't afford to do that. Or maybe you can, I don't know. $700 per shot. So spend insane amount of hours mowing through this. You see that U sub also pops up here and there. Do all of the problems in the textbook. You don't have that many, about 60. And we did few. No, I lied. 42, and I did. You have 42 problems to deal with, and I probably solved, out of those 42, I probably solved whatever over here, 10 maybe. So try to work them out, and then use Mathematica to check the answer. Well, what Mathematica? Just take the derivative. It's a product rule. Take the derivative. Here, take the derivative right there. Make sure that this is equal. When you take the derivative of this, make sure you get this. Go. That's how you check. Obviously, Mathematica is going to do it for you, but if you are on the exam and let's say you care, right? You're done with integration, you immediately check by the derivative, and you know if it's right. So differentiate 1/2 e to the x sine x minus cosine x. Plus c, who cares, because derivative of plus c is 0. So and you should do this for every problem. So copy the first, which is 1/2 e to the x, times derivative of the second, which is derivative of sine is cosine x, and derivative of negative cosine is exactly, very good, plus the derivative of the first, which is still 1/2 e to the x, and then copy sine x minus cosine x. There you go. So what do we have? The cosines will cancel, exactly, and you have 1/2 plus 1/2 is 2/2, which is 1. So e to the x sine x. That's exactly what you have to get, right there. Now this is how you know that what you did is 100% good every time. And this is the reason why I loved exams 1 and 2 when I took Calc 2 as a student. And I liked it more than Calc 1 because in Calc 1 you don't really have way to check. Unless you're working on tangent line, you graph both and you make sure they touch and all that kind of stuff. But when you do the derivative, you don't really have the way to check. When you integrate, you can always take the derivative, and if you get what you started from, perfect. If you don't, something is wrong. You check the check first, and then if you're 100% sure that you did the derivative correctly, then something is wrong with the problem. And you can go back to every example we did tonight, do the product rule off of the answer, and verify that that was good. So that takes care of this lecture. I don't have time to lecture the entire trig, but I will give you the intro of things that you need to ruin your weekend with so that you can survive the next 2 lectures, which are trig integrals and trig substitution. So that's coming up on Monday. So let's restart the stream for that very important announcement.